Everyone's talking about AGI like it's just around the corner. Scale up the models, add more parameters, throw more compute at the problem, and eventually we'll stumble into artificial general intelligence through brute force. What if I told you that approach is not just wrong, but actively preventing us from building truly intelligent systems? Subscribe for the technical deep dive that might change how you think about AI entirely. The scaling hypothesis has given us some incredible capabilities. Language models that can write, reason, and converse in ways that seemed impossible just a few years ago. But there's a ceiling we keep hitting, and it's not about data or parameters or training time. It's architectural. These models are what computer scientists politely call paradoxically shallow. Despite their enormous size, they're computationally constrained to solve only certain classes of problems. They literally cannot perform the kind of iterative, deep reasoning that complex problem-solving requires. Researchers have been documenting these limitations, testing these models on reasoning benchmarks, watching them fail at tasks that require genuine multi-step thinking. But the industry keeps doubling down on scale because, well, that's what's been working for everything else. The alternative? Building AI that thinks more like brains actually work. Hierarchical, multi-time scale, dynamically adaptive. Turns out that might be the missing piece. Think about how you solve a complex problem. Let's say you're planning a cross-country road trip. You don't immediately start calculating precise GPS coordinates and gas mileage calculations. Instead, your brain does something much more elegant. First, you think big picture, west coast to east coast, maybe hit some national parks, avoid winter weather. That's your high-level strategic planning happening. Then, once you've got that framework, your brain dives into the details. Specific routes, hotel bookings, daily mileage targets. Two different types of thinking, operating at two different timescales. Your brain literally has neural circuits that work this way. The thing is, most AI systems today operate in basically one mode. They're pattern-matching machines that apply what they've learned in training. They don't have this dynamic interplay between strategic thinking and tactical execution that makes human reasoning so flexible and powerful. Traditional AI approaches try to capture this with something called chain-of-thought prompting, basically getting the AI to think out loud by generating step-by-step reasoning. And while that works better than just asking for an answer, it's still fundamentally limited. The real breakthrough comes when you build this hierarchy directly into the architecture itself. Let's talk about why our current AI hits these walls. Transformers, the architecture behind GPT, Claude, all the big language models, they're what computer scientists call fixed depth. Every time they process a token, they do exactly the same amount of computation. Whether you're asking them to add 2 plus 2 or solve a complex logical reasoning problem, they get the same computational budget. This constraint puts these models in something called the AC0 complexity class. Sounds technical, but what it means is they can't do deep, iterative thinking that complex reasoning requires. This isn't just a theoretical limitation. In practice, when researchers test these models on tasks like complex Sudoku puzzles or maze navigation, they don't just struggle, they fail completely. Meanwhile, a 27 million parameter model designed with hierarchical reasoning can solve these same problems nearly perfectly. That's not a small difference. The issue isn't scale, it's architecture. We've been trying to solve intelligence by making bigger hammers when what we actually need is a completely different kind of tool. So what does a hierarchical reasoning model actually look like? Picture two AI systems working together, but in a very specific way. The high-level module is like the strategic planner. It operates slowly, updating its state only after the low-level module has done a bunch of work. This module is responsible for what researchers call empathetic processing, grasping the essence of a problem, understanding context, figuring out what approach might work best. The low-level module is the execution engine. It's fast, reactive, good at applying algorithms and pattern matching. For every slow update from the H module, the L module might do dozens or hundreds of fast iterations. They work in this nested loop where the L module basically gets an assignment from the H module, goes off and works on it intensively until it reaches what mathematicians call a fixed point, basically a stable solution, then reports back. The H module looks at the results, updates its strategy, and gives the L module its next assignment. The clever part is something called adaptive computation time. The system has a built-in mechanism that decides when it's done thinking about a problem. Easy problems get solved quickly with minimal iterations. Hard problems get more thinking time. And unlike traditional recurrent neural networks that require storing every intermediate step in memory, which gets expensive fast, HRMs use a technique called one-step gradient approximation that maintains constant memory usage no matter how long they think about a problem. This isn't just more efficient, it's actually more biologically plausible. Real neural networks don't do backpropagation through time the way artificial ones do. They update based on local information and current states. HRMs work more like actual brains in this respect. The result is a system that can perform what the researchers call latent reasoning, complex multi-step thinking that happens entirely within the model's internal state space, without needing to externalize every step as text tokens. It's thinking, not narrating. The performance differences are honestly wild. A hierarchical reasoning model with 27 million parameters trained from scratch on just 1,000 examples scores 40.3% on this benchmark. Claude 3.7, 21.2%. OpenAI's O3 Mini High, 34.5%. Keep in mind those models are orders of magnitude larger and were trained on vastly more data. On complex Sudoku puzzles, HRMs achieve near-perfect accuracy. State-of-the-art chain of thought models, they fail completely. And this gets to the heart of why this approach might be fundamentally different. When researchers looked more closely at what was driving these performance gains, they found something unexpected. It wasn't necessarily the specific H-module, L-module architecture that was doing all the heavy lifting. It was the iterative, recurrent processing. The fact that the model's output gets fed back into itself for progressive refinement. This tells us something important. The breakthrough isn't just about mimicking brain structure. It's about enabling iterative, adaptive computation, the ability to revisit and refine solutions rather than being locked into whatever comes out of a single forward pass. The applications where hierarchical reasoning really shines are exactly the ones where current AI falls flat. Multi-step reasoning, planning, anything that requires working through a problem systematically rather than just pattern matching from training data. Take robotics. Current robotic systems using large language models can understand commands and generate reasonable-sounding plans, but when it comes to actually executing complex, multi-step tasks in the real world, they struggle. You need the kind of hierarchical task decomposition that HRMs naturally provide. Strategic planning at the high level, real-time motor control at the low level. But probably the most exciting application is in what researchers are calling agentic AI. Systems that need to plan and execute complex, goal-oriented sequences of actions over extended time periods. Think AI assistants that don't just answer questions, but actually help you complete multi-day projects, manage complex workflows, coordinate with other systems. The efficiency gains matter here too. HRMs can run on single GPUs instead of requiring massive server farms. That means you could potentially have sophisticated AI agents running locally, on edge devices, in robots, in autonomous vehicles. It's the difference between AI that lives in the cloud and AI that can go wherever you need it. But let's be realistic about the limitations here. Hierarchical reasoning models aren't magic, and they come with their own set of problems. The biggest issue is interpretability. Yeah, having hierarchical structure gives you more visibility than completely flat architectures, but understanding exactly what's happening in these nested loops is still really challenging. The black box problem doesn't go away just because you've organized your black boxes into a hierarchy. There's also this fundamental question about whether hierarchical behavior actually requires hierarchical mechanism. Some cognitive scientists argue that what looks like hierarchical reasoning might actually emerge from simpler, non-hierarchical processes. Statistical learning, pattern matching, that kind of thing. So we might be building elaborate hierarchical architectures to solve a problem that has simpler solutions. Current HRMs also don't handle long-term memory particularly well. They're great at deep thinking within a single problem. They don't naturally integrate information across different tasks or remember things over extended periods. For real AGI, you need systems that can think long as well as think fast and slow. Training hierarchical systems is more complex than training standard neural networks. Debugging is harder. Integration with existing systems requires rethinking a lot of infrastructure. The efficiency gains are impressive, but they come with engineering complexity. Here's what gets me excited about hierarchical reasoning as a path toward AGI. It's not just about building better AI, it's about building AI that thinks more like we do. Human intelligence isn't just pattern matching at scale. It's this dynamic interplay between different types of cognition, operating at different timescales, handling different aspects of problems. We have intuitive understanding and systematic analysis. We can think fast when we need to, and slow when the situation demands it. Hierarchical reasoning models suggest a path toward more flexible, more adaptive intelligence. Systems that can dynamically allocate their cognitive resources based on what a problem actually requires. That can switch between different modes of thinking depending on context. And the efficiency gains matter for AGI too. Real general intelligence needs to be deployable, accessible, able to run in diverse environments. If your path to AGI requires massive data centers and enormous energy consumption, then you've built something that's fundamentally limited in its applications. The brain runs on about 20 watts of power. That's the gold standard for efficient intelligence. Look, I don't know if hierarchical reasoning is the silver bullet for AGI, but it's addressing real, fundamental limitations of current AI in ways that just throwing more compute at the problem isn't. The fact that a 27 million parameter model can outperform billion parameter models on complex reasoning tasks should make us all pause and reconsider our assumptions about what intelligence actually requires. Maybe the path to AGI isn't about building bigger brains. Maybe it's about building better organized ones. If you found this deep dive useful, subscribe for more explorations into where AI is actually heading. Not just the hype, but the real technical breakthroughs that might change everything. The future of intelligence might be more structured than we thought.